In this video, we're going to talk about how we can verify if two things are inverses. And again, remember that what we mean by inverses, if an original function carries you from an x value to a y value, then the inverse would carry you from a y back to the x. Graphically, ways that we can verify two things are inverses. Two functions are inverses if their graphs are reflections in the line y equals x. And this actually goes back to some geometry, and I don't know if you'll remember this, but we talked about how to reflect something across the line y equals x, how to reflect a point directly across it, and the method was, if you have an original point xy, the rule was to flip it across the line y equals x, then it turns into yx, which oddly enough looks identical to what we're doing. Two functions are inverses if the original xy turns into yx. So therefore, we can look at the graph then. If this is the case, if they are reflections across the line y equals x, then they would have to be functions for that reason. So this is find each inverse, or find the inverse of each function, then verify graphically that we are correct. So again, the way we find inverses, this is y equals 3x minus 6. I'm going to switch it to x equals 3y minus 6. Instead of rewriting it, I'm just going to go ahead. This is y, so switch it to x and switch this to y. So there's your inverse. Let's move our 6 over by doing x plus 6 is equal to 3y. Let's divide everything by 3. Let's put a 1 in front of that x so we will have something to divide. And you'll have 1/3 x plus 6 divided by 3 is 2. So that should be our f inverse. Now let's verify that graphically. We'll graph both of them. My original function is y equals 3x minus 6. So that's a slope-intercept form, 1, 2, 3, 4, 5. Let me actually zoom in to graph y equals 3x minus 6. Now I've actually written both of our functions here so we can see them better. So 1, 2, 3, 4, 5, 6. My slope is 3, so let's plot some more points. That's not far enough. So there is my original graph. Now let's plot my new inverse function. Let me connect my dots first on this one. And there's my connected lines. My inverse function is 1/3 x plus 2, so y-intercept of 2, rise and run 1/3 for a slope, so down 1 over 3. Let's do a few more points. Again, the rule is once I connect these dots, if they're reflections across the line y equals x, then they're going to be inverses. So what I've done here is I've graphed both lines along with the line y equals x there, and you can see that every dot are perfect mirror images across this line. And you can check it as well, like this dot here is going to be the point 0, 2, and guess what this one is? 2, 0. This point here and this point here will just be a perfect xy flips of each other. Next problem. Your original function is y equals x to the third plus 4. So your inverse is going to be x equals y to the third plus 4. First step, move the 4 over. That'll be x minus 4 equals y to the third. So our inverse should be the cube root to get rid of the third. Cube root of x minus 4 is equal to y. So we're going to call that our f inverse. So now let's graph both of these and see if we're right. So to graph these, we can do it a couple of different ways. We can actually use transformations if we want to. Our original graph is x to the third. If you want to just transform that up 4 units, that's fine. Or we can do a table of values. Plug in 0, you get 4. Plug in 1, you get 5. Plug in 2, you would get 8. Let's see, 8 plus 4 would be 12. I don't think that'll fit. It'd be somewhere up here. Plug in -1, you would get 3. So my graph would look something like this. And again, if you would like more points, you can plug in -2. That'd be -8 plus 4, which would be -4. 1, 2, 3, 4. So there's my first graph. It's going to look something like that. And I'm going to go ahead and graph my y equals x line. Okay, now to graph my second line, now I've got to be careful about what I plug in for my x's because I really need to know values that I plug in needs to be things that give me what I know the cube root of. Like I know the cube root of 8, I know the cube root of 1, and I know the cube root of 27. That's my perfect cube roots. So what I could actually do there is I could plug in a 5. and that's going to give me the cube root of 5 minus 4, which is cube root of 1. So I know 5, 1. I can plug in a 12, and that would give me the cube root of 8, which I know is 2. I can plug in some negative values because I actually also know those, the cube root of the negative 1, and I also know the cube root of negative 8. So if I were to plug in a 3, that'd give me the cube root of negative 1. If I were to plug in a negative 4, that'd give me the cube root of negative 8. Now let's plot these points. And here you can see my second graph, and you see that, again, they are perfect mirror images across the line y equals x. Okay, now another method is how can we verify these algebraically? Now here's the rule. F and g, two functions, will be inverses only if f, f of g is equal to x and g of f will equal x. So we're actually going to use compositions to determine if two functions are inverses of each other. Number 3 says verify algebraically that these are inverse functions. So let's find f of g first off. If you can't remember how to find f of g, we're going to find f of g. We're going to plug g into f. So I'm going to take f, which is x minus 7 divided by 2. In the place of x, I'm going to put 2x plus 7. These parentheses are really unnecessary, so now let's clean it up. Plus 7 and minus 7 cancel and leaves you with 2x over 2, which is x. So there's f of g, so now let's find g of f. So we're going to take g, which is 2x plus 7, and in the place of x, I'm going to put x minus 7 over 2. When you multiply 2 over 1 times that, the 2's cancel and leaves you with x minus 7 plus 7. And when that cancels, you also get x. So since f of g and g of f are both equal to x, these are inverses, and you could check that graphically as well. Number 4. Now the reason they put this restriction here is because x squared minus 5 looks like this, and it would not have an inverse unless you restrict it only to one side of that parabola. Then it's invertible. So that's the reason they put that restriction there. And you can actually see that same restriction being applied here because that square root of x minus 5 is going to have a domain restriction as well. But that part doesn't really matter here. Let's find f of g. So we're going to take f, which is x squared minus 5, and in the place of f, or in a place of x, I'm going to put in my f. When you square a square root, it gets rid of it, so that'd be x plus 5 minus 5. Those would cancel and leaves me with x there. Now let's find g of f. So we're going to take our g, which is the square root of x plus 5, and in the place of x, we're putting x squared minus 5. Parentheses there would be unnecessary. Plus 5 and minus 5 are gone. Leaves you the square root of x squared, which is also x, so these two functions would have to be inverses. Okay, number 5, find f of g. So we're going to take we're going to take f, which is x plus 3, divided by 2x. In the place of those x's, we're going to put 3 over 2x minus 1. So this one might be a little bit trickier. 3 over 2x minus 1. Now let's see if these are inverses. These parentheses are unnecessary, but we are going to have to find common denominators. So let's multiply top and bottom over here by that 2x minus 1. You can put those in parentheses if you'd like. So on top we now have 3 plus 6x minus 3. I went ahead and distributed that positive 3 over 2x minus 1. And then on bottom we have 2 over 1, which would be a 6 over 2x plus or 2x minus 1. So that's going to be 3 minus 3 cancels and leaves me with 6x over 2x minus 1 divided by. Okay, now to divide two fractions, we flip the second one and we change division to multiplication. 2x minus 1s actually cancel each other out. And here, since there's no plus or minuses, I can cancel the 6 with a 6, and oddly enough, you get x. So f of g, we have now proven is equal to x. Now let's do g of f. Okay, to find g of f, which is 3 over 2x minus 1. And in the place of x, I'm putting x plus 3 over 2x. Maybe this one will be a little bit easier. To multiply here, the 2's would cancel, and it leaves me with 3 over. On bottom, I have x plus 3 over x minus 1. That 1, we're going to have to find a common denominator so I can subtract it. So we're going to multiply top and bottom by x here. So that actually turns 1 over 1 into x over x. So now I now have 3 over my common denominator of x on bottom. I have x plus 3 minus x. The x and the x would cancel. And now to divide these two things, I'm going to take my 3 on top, and I'm going to flip and multiply by the reciprocal of the bottom. 3's cancel, and it leaves you with x. So these two functions, since f of g was x and g of f is also x, these two functions would be inverses. Okay, the next example says find the inverse of each function. State any restrictions in the domain, verify graphically and algebraically. So here we go. First off, there's no domain restrictions. You can find the cube root of anything. So the inverse of this, let's switch our y. Let's turn it into x equals the cube root of y plus 2. Next step, move your 2 over. That'd be x minus 2 equals the cube root of y. Last step, to get rid of a cube root, we're going to take the other side and raise it to the third power. And that's going to equal f inverse. Just write it backwards there. Let's verify that this is indeed our answer graphically. And let's do it a little bit different, just to show you that we can always use Desmos as well to verify these graphically. Okay, and you're going to see how easy it is to use Desmos to do this. So I've graphed both of these, x to the third, cube root of x plus 2, and x minus 2 to the third. Now I did have to, I used a trick here. Instead of the cube root of x, notice that I wrote this as x to the 1/3 power. If you go back and remember your rational exponents, I graphed that along with x minus 2 to the third, and I even graphed y equals x here just to show you that definitely those two functions are mirror images in the line y equals x. So there's graphically, we have verified it. So now let's verify it algebraically. So if our two functions are f of x equals, and there it is, f of x equals cube root of x plus 2, and g, I called my second function g of x just to save the notation of now I can say f of g and g of f. So f of g is going to be the cube root of x plus 2, and in the place of x, I'm putting inside of here x minus 2, and I'm just going to write it like this, x minus 2 to the third power. So when we find the cube root of a third power, that leaves you with just x minus 2, and you have your plus 2 on the outside, which does leave you with just x. When you find g of f, so let's take x, and in the place of x there, I'm putting my other function, so I'm putting the cube root of x plus 2 right there, and we don't really need parentheses around it. These cancel and leave with the cube root of x to the third, and the cube root and third power cancels and leaves you with just x. So therefore, there's our verification algebraically. Next function, now they've given you a domain restriction here because, again, this is a parabola, and you're going to have to restrict it to one side or the other in order to make it invertible. So there's our original function. Now what I would do is I would go ahead and find the range of that function as well, which is actually going to be pretty easy for parabolas if you think about it. This parabola has been shifted left 4 and down 2. So it looks like this. And you're only going to graph the right side. And we want to know if the domain, if we're only talking about the right side, what would be the range? Well, since we know this is the vertex, we already know what the range is anyway. So let's get rid of the left side. And the range would be from that y value up, from the vertex up. So if my vertex is located at -4, -2, then my y values will always be above -2. So there's your domain and range of your original. Now let's invert it. So if your original is y equals, your inverse will be x equals, instead of x plus 4, we now have y plus 4 squared minus 2. Move the minus 2 over by adding 2 equals the square root of y plus 4 squared. To get rid of a square, we're going to plus and minus. Now we got to be careful with that plus and minus. I just want to keep you in a habit of putting plus and minus there. And then we move the 4 over by doing -4 plus and minus the square root of x plus 2 equals f inverse, or equals, yeah, we'll go ahead and put f inverse. Now let's examine that a little bit closer though, because I'm going to have to get rid of that plus and minus, because we need, okay, the domain and range here. The domain here, the x values are now going to be the range of the original. X is going to be greater than or equal to -2, but I need my y values to be greater than or equal to -4. That's going to be my domain and range of my final function here. In order to get my range to be this, if I don't take away this minus sign, -4 minus things is going to make things smaller. But if I want to keep my y values greater than or equal to -4, -4 plus square roots, that's going to keep it bigger than -4. So when you're restricting these domains, you're going to have to do that. So let's graph our two functions. And you can do a table of values. It's very similar to, since we're restricting it, it's very similar to what we did with piecewise functions. Let me draw me a line here at x equals -4. We're going to do, we're only going to draw values to one side of it. We're only going to draw values on the right side of that -4. So first value is going to be -4, -2, which is going to be the vertex. And then you can just do you a table. You can plug in x and y. You can plug in -3, -2, -1 and see what you get. And there's your y values. And then just plot them. Let's see, you got -1, 2, 3, -1. You've got -2, +2. And you got -1, +1, 2, 3, 4, 5, 6, 7. So there's my graph. And again, notice I only graphed it to the right of -2. Now let's work on our inverse graph down here. And also, since my domain, I'm only graphing things to the right of -2 now. Let's go ahead and do us a new line. So let's do us a new table of values as well. We're only graphing things right of -2, so that'd be like -2, -1, 0, and 1. Plug those values into our inverse to graph it. Or we probably should have thought about this. -2 will be fine. You'll get the square root of 0 plus -4, that'd be -4. However, we should have used values that we know the square root of. So let's take some of these away. Inside of my square root, I have x plus 2. Let's see, I know the square root of 1, so I could plug in a -1. That one would be fine. I know the square root of 4, so let's plug in a 2. So I have 2 plus 2 is 4. I know the square root of 9, so I can plug in a 7. So always be careful what you're plugging in. And there you see my y values that I get when I plug them in. So now let's plot those points. I'm going to do it in red again. So -2, -1, 2, 3, 4. I'm only going to graph, again, values to the right of that. My next one was -1, -1, 2, 3. The next one was 2, -2. And then finally I had 7, -1. So 1, 2, 3, 4, 5, 6, 7, -1. Connecting those dots and then drawing my line y equals x. And you can see again, definitely those are inverse of each other. They're mirror images. Now let's try to verify it by algebra. So there's my two functions. Let's find f of g. This should be pretty easy to plug in. So we're going to take f, which is x plus 4, squared minus 2. And in the place of the x, I'm going to put -4 plus, I actually should have took away that plus and minus, -4 plus the square root of x plus 2. I can write it like that because these are going to cancel anyway. And you have now the square root of x plus 2 in parentheses squared minus 2. A square root and a square undoes each other. You have now x plus 2 minus 2, which leaves you with just x. Then f of g, or excuse me, g of f would be, let's take g, which is -4, plus the square root of x plus 2, and in the place of x, we're putting x plus 4 squared. Erase that. Minus 2, and the -2 and +2 cancel. The square and square root will cancel and leaves you with -4 plus x plus 4. -4 and a +4 also cancel and leaves you again with just the x. Okay, the next one, number 8. First off, let's find the inverse, and this does have a domain restriction. We just need to make sure that x does not equal 0. So we have y Instead of y equals, we now have x equals 5 over y minus 2. Let's move our 2 over. So I have x plus 2 equals 5 over y. I'm going to get rid of my y by multiplying by it. So I'm going to come up here and do times y. And then I'm going to get rid of the x plus 2 by dividing by it. So there's my new function. So y is equal to 5 over x plus 2. We can now call it f inverse. Let's graph both of these. Okay, now we see here's Desmos. We'll use it again. And I've graphed both of them, and they are perfect mirror images across that line y equals x. So now let's go back and let's try to verify them algebraically. So let's write down our two functions again. Okay, number 8. You have y equals 5 over x plus 2. So we do have a domain restriction here. X just can't be 0 because there will be that asymptote line there. This is a transformation of the function 1 over x. We know what it looks like. So in order to find the inverse, we're just going to do x is equal to 5 over y plus 2. We're going to move our plus 2 over by doing minus 2 equals 5 over y. Now we can treat this like a proportion and put this over 1, or we can just simply, since we have division by y, mark it out, and we're going to come over here and we're going to multiply by y. Now the easy way to now get y by itself is, since these are being multiplied, let's now take the x minus 2 and move it back over by dividing by x minus 2. So there's going to be hopefully the inverse function. So we'll put f inverse is equal to this. Now what I've done is I have taken and I've graphed both of these, which, by the way, x for your inverse cannot be 2. So I've graphed both of these. So let's, instead of graphing them on here, let's use Desmos and let's verify them graphically. And you can see that both of those are perfect mirror images, the blue and the black, across the line y equals x. So finally, let's verify algebraically that's also the case. So let's write down our two functions. And there they are. Let's find f of g and g of f. So to find f of g, take your f function, which is 5 over x plus 2. And in the place of x, we're going to put 5 over x minus 2. To clean that up, we're going to have to flip and multiply. This will be 5 over 1. So we're going to do 5 over 1 times x minus 2 over 5. The 5 and 5 cancels and leaves me with x minus 2 alone, and then plus 2, and those cancel and leaves you with just x. So therefore we see that f of g is x. Now let's find g of f. G of f, we're going to take 5 over x minus 2, and in the place of that x, we're putting 5 over x plus 2. Plus 2 and minus 2 cancels, and it leaves you with 5 over 5x. To divide those, we're going to flip the second one. There's the top one. We're going to flip the second one and multiply. 5s are gone and leaves you with just x, so therefore they are inverses of each other. And the last one. We do have a domain restriction here. X has to be, since the x plus 3, the stuff under radical has to be greater than or equal to 0. That means that x has to be greater than or equal to negative 3. So your domain would be from negative 3 to infinity. Again, I like to find the range, so that's going to tell you the domain of the inverse. So the range of this, since x has to be bigger than negative 3, as you plug those values in, negative 3, negative 4, negative 3, negative 2, negative 1, 0, you'll find out that you get values at 0, and then they start getting increasingly bigger. So your range is going to be from 0 to infinity. So your inverse is going to be x is equal to 1/2 square root of y plus 3. Step number 1, since this is being multiplied by 1/2, you're going to divide by 1/2, which is the same thing as multiplying by 2. To get rid of a square root, we're going to square the other side. And I'm going to go ahead and square it as I'm writing it down. Square the 2 and square the x. And finally, we're going to move the plus 3 over by subtracting 3. 4x squared minus 3 is equal to y. And that should be your inverse. Now let's look at the graphs of each. Now we've got to be careful because this does have a domain restriction. The domain of your original is the range of your new. The range of your original is going to be the domain of the new one. So we're only going to graph this from 0 to infinity. So that's going to be the domain of this function. So now let's look at the graphs of both. Okay, something I do want to point out about our graphs here. Again, when I'm graphing the square root of x plus 3, I try to pick things that I know the square root of. So what I plugged in there was I know the square root of 0, so I plugged in -3. I know the square root of 1, so I plugged in -2. I know the square root of 4, so I plugged in 1. And I know the square root of 9, so I plugged in 6. So that was the values that I plugged into my original. And then the values that you get, if you want to, like when I plug in -3, I get 0. So since I got 0, you can actually take and plug 0 into this, and it should be the point that goes along with this point. Okay. So there it verifies, you see the mirror images, so they are definitely inverses of each other. Now let's copy down our two functions over here and verify it algebraically. So when you find f of g, let's take our f function, 1/2 square root of x plus 3, and plug in 4x squared minus 3. Minus 3 and plus 3 will cancel and leaves you with the square root of 4x squared. That'll be 1/2 times the square root of 4, and the square root of x squared will be 2x. Half of 2x will be a single x. So there's f of g. Now let's find g of f. So that'd be 4x squared minus 3. In the place of that x, again, we're plugging in 1/2 the square root of x plus 3. We're going to have to square everything in those parentheses. So that's going to be 4 times 1/2 times 1/2 is 1/4. To get rid of, or when you square the square root, it's going to get rid of it. So now that's what we have. So you have 4 times 1/4. That's actually going to cancel each other out and leaves you with x plus 3 minus 3, and the plus 3 and minus 3 leaves you with just the x.